Chandrasekhar lecture was initiated by the Center for Strings, Gravitation and Cosmology about 4 years ago. The motivation for initiating the lecture was to create an opportunity to highlight recent developments in the fields of gravitation, particle astrophysics, semi-classical and quantum gravity, as well as cosmology. We have held 8 Chandrasekhar lectures earlier. We are honored to have with us today Professor Joseph Silk from the Institute of Astrophysics, Paris, and the Johns Hopkins University in the US to give the 9th Chandrasekhar lecture. In today's lecture, Professor Silk will be speaking on current and future prospects for the CMB. Before I invite Professor Silk to give the lecture, let me say a few words highlighting his contributions. Professor Silk is Homewood Professor of Physics and Astronomy at the Johns Hopkins University, Baltimore, and Emeritus Researcher at the Institut d'Astrophysique, CNRS, and Sorbonne University, Paris. He was the Savilian Professor of Astronomy at the University of Oxford from 1999 to 2011, where he is currently a Senior Fellow at the Beecroft Institute for Particle Physics, Particle Astrophysics and Cosmology. He previously was Professor of Astronomy and Physics at the University of California at Berkeley. Most of his scientific research is related to cosmology and particle astrophysics, including the CMB, galaxy formation, and dark matter. He is the author or co-author of more than 800 papers in refereed journals, 7 popular books, including The Big Bang and Back to the Moon, which was published in 2025. He has supervised more than 35 PhD students and more than 90 postdoctoral researchers. He is a Fellow of the Royal Society, the American Academy of Arts and Sciences, and the National Academy of Sciences. He has received various awards, including the Gold Medal of the Royal Astronomical Society, the Bakerian Lectureship of the Royal Society, the International Balzan Prize, the Henry Norris Russell Lectureship of the American Astronomical Society, the Gruber Prize in Cosmology, and the Amaldi Award of the Italian Society for General Relativity and Gravitation Physics. He is a Fellow of the American Physical Society, the Institute of Physics, the Royal Astronomical Society, and an honorary member of the French Physical Society. I now invite Professor Joseph Silk to deliver the Chandrasekhar lecture. Let's give him
And it's been delightful to come back here and revisit old friends, and I really appreciate the hospitality that I find here. Anyway, so this is going to be, I'm going to begin with something slightly historical to reflect a little bit on how I entered the field of cosmology. And I just want to stress right now, and you'll see why at the end of my lecture, that this lecture is particularly addressed to the young people in this audience. And that's because, as you'll see, the timescales for doing what we want to do in cosmology are very long indeed, which has implications for some of us. But, you know, we have to lay the foundations, and that's what I hope to show you now. So let me begin by saying a few words about the inspiration I got, pictures of the giants in the field of cosmology. Presumably you will recognize these people. Okay, so they've set the scene for what we do now. Here are their names. So from Einstein onwards, these have laid the foundations for everything we do. To understand the beginning of the universe and more recent developments and how structure formed in the universe. Okay, so it's an ongoing process, of course. So let me start with how I entered the field, really. This was my inspiration. It still is everyone's inspiration in the field. What you can see in this map of the history of the universe are the various epochs that take us from the beginning, the mysterious epoch of how everything began with inflation, which I'll come back to. When we look back at the microwave background, we can see the seeds of all the present structure, and as time goes on, that leads to galaxies like our own. And we try to understand all of this as best we can. And the basic idea is that it's a hierarchy. Small clouds assemble into bigger and bigger clouds. This is our basic theme of modern cosmology. And these clouds contain dark matter and baryons, ordinary matter, and eventually assemble into galaxies like our own. And when we look back at the microwave background, we see this fossil radiation, which really inspires this picture. When the universe was 380,000 years old after the Big Bang. Now, there are two big question marks, and I'm going to address both in this lecture. Is what happened at the beginning? How did things begin? And the other is, what about the Dark Ages? Here, before there was anything, well, there was something there. There was hydrogen, because and dark matter too. Dark matter is harder to see, but hydrogen is not. In principle, we can do that, and it should have fluctuations in, because from these fluctuations, seeded by what happened earlier, the galaxies began. And so those are the things that I will be talking about in the next hour or so. Okay, let's begin then. So this is, I entered cosmology at a very fortunate time, very lucky time really. I began as a graduate student in the very same year really that the microwave background was discovered. And so suddenly, it's in some ways, if you're dealing with something new, it just makes a huge advantage, because you're not entering a field that's been mined by many eminent scientists before you. And I was lucky that there was the microwave background, cosmic microwave background. And this was, of course, a major stir at the time. And I was a graduate student, and this is a summer school that I was at when I first began working as part of my thesis topic on the formation of structure in the universe, formation of galaxies. That was my thesis. And on here you'll see some, famous astronomers. I will, but I am somewhere here, right over here. It was a summer school. I was learning, and I began a project at that school. This is in Woods Hole in the US. And then a year or so later, I wrote my first paper. And this was on the notion, really, that this fossil radiation from the Big Bang, which preceded, to some of us at the time, it was obvious it preceded everything else, in the simplest models we had then, it should contain some evidence of the structures that formed later, notably fluctuations in the radiation field that would eventually seed the galaxies. And so that was basically what part of my PhD program. And I was, as I said, it was a fortunate time, because one could start off with very simple calculations to do something quite new, which had some impact later on. Okay, anyway, so that was in 1967. Now, to give you some idea of the timescales, there were many experiments over the years, but they were all rather primitive. It was only with the first space satellite telescope to look at the relic radiation that we made the real discovery. And so this happened in 1992 with the COBE satellite, Cosmic Background Explorer, and it made the first maps of the sky and detected fluctuations from the beginning. Now, it was a small telescope with very low angular resolution, so it didn't quite see the seeds that we expect in the galaxies, but it did see the seeds of the larger structures, the much larger structures. And it made a great sensation at the time. This was something quite new. It was an expectation of the Big Bang, and so you can see it made front page news at the time. It's unusual to have a science discovery on the front page. What you see here is the Milky Way itself masked out, that's full of dust, and this is a radio map, a microwave map of the sky, mapped by this satellite after a year or so of observation. And so, and you can see the irregularities, the fluctuations, and large patchiness, and those are the seeds and smaller ones that you don't see that were not resolved by this telescope, which we inferred must be there too. So that was big news. And of course, in England, they have an even bigger picture on the front page of this newspaper. It was spectacular. It's rare, I think, to see science discoveries have such big headlines. So that was sort of a unique time, an inspiring time also for people who worked on cosmology. So it led to this. The person who designed the telescope and the person who designed the spectrometer on that system received the Nobel Prize some years later for their discovery. And so this really is what set the seeds for modern cosmology. Time this was being done before we, and indeed for years later, cosmology was very much, it was definitely a branch of physics, but maybe not the most precise branch of physics. Everything we talked about was uncertain by at least factors, like 50% or something, when we tried to measure the universe. And it's only as telescopes like this and its successors developed that we learned how to do better. So let me just show you the inspiration that led to this telescope and to what it was trying to do. So in this, we call this a space-time diagram, and what you can see is here we are at the moment, and we're looking back. This is the regime in time where the galaxies are, and then before galaxies there were the dark ages, okay? And then before the dark ages, the radiation, it was like a fog in the early universe where the radiation comped and scattered off the ionized electrons. Then finally the universe went neutral and the radiation came straight to us from what we call the last scattering surface. And so that then meant that, for example, when you look in different parts of the sky, and so you're looking back here, you see patches in the sky that are not causally connected to each other at that time. They're independent. This is our light cone looking back. And what this means is that to explain the origin of those blobs that the COBE satellite found, you had to resort to the quantum theory, quantum fluctuation, quantum cosmology basically to drive these, because there was no physics, no causal physics that was able to connect them. And so the thought almost from the beginning was that we were seeing, of the experimental discoveries, was that we were seeing something very important, which at the time, of course, we were far from understanding. So the dark ages in between the galaxies and the last scattering fluctuations that we see in the microwave background are one huge unknown. And the beginning, how the universe got to be its present size, we call the theory of that beginning. Most of us call it inflation theory. Those are our two major targets in cosmology. And in this talk, I'll try to show you how they're actually connected, and that solving one will eventually lead to us solving the other, as we'll see in a moment. Okay, here is what you can imagine then is the big picture with a slightly more precise way of looking at it. So in this diagram, you can see us here and now, some 10 billion years after the beginning, with a universe full of galaxies and so forth. And as we look back in time, light comes to us from these fluctuations 380,000 years after the Big Bang, actually, something like that, and comes to us, and we see these fluctuations. We make maps of these. And in between, we have the region where all the galaxies are forming in this region, labeled by gravitation, by gravitational instability, we call it. And then before then, there were the dark ages, where there was nothing but hydrogen clouds that we're still very far from detecting. And then going back, because of all this radiation scattering off the ionized plasma in the universe, we can see nothing directly, but we infer there certainly was a beginning, and our current theory, developed in the 1990s, is there was a period of inflation, which I'll talk about a bit more later, in which the universe grew rapidly for a fraction of a second to reach its present size, and then things proceeded in the normal way as we infer in the standard understanding of general relativity and cosmology, expanding as it seems to expand. Eventually the fluctuations that were present from the beginning getting stronger as time went on because of the effects of gravity, and eventually gravity became important enough for the fluctuations in density to actually collapse on themselves and turn into giant balls of baryons and also dark matter particles probably, which finally form the galaxies. And so that sort of is our scenario, and we are trying, we're going to try in this talk to understand really what happened before the galaxies formed, before these clouds formed into galaxies. Can we see any evidence of the dark ages to confirm this picture? It's really the missing link. Now we've seen these radiation seeds. What about the matter is the question next, and that we're trying to fill in now. And then what on earth lies, this is a wonderful theory, the theory of this incredibly rapid expansion for a tiniest fraction of a second, but what is the proof that this actually occurred? This theory of inflation, and we'll come to that too in a moment, how we can try to test that. Okay, so again, to start with a slight bit of history again, the data's come along incredibly well. And so in this picture you can see an early result from, essentially from my PhD on the formation of the galaxies, in which you see for some particular scale that we're studying that might eventually be a galaxy, you see the difference in the growth, in the strength of the clouds, the fluctuations really initially, that were in three different components of the universe. There was the dark matter, which is non-interacting, and we assume it's there. We haven't found it yet, but it's the assumption of what we call standard cosmology, and the baryons, which is the stuff we're made of, and of course the radiation that we measure. And the radiation is strongly coupled to the baryons by Compton scattering early on, and the dark matter is not coupled. And the fluctuations of the dark matter continue to grow under gravity, but the radiation is sort of pinning the baryons down, as it were, because they're scattering. And so eventually, because effectively the sound speed in a radiation plasma is so high, you basically have essentially sound waves in a matter radiation plasma, and they eventually get smoothed out by friction between radiation and baryons, basically, and you're left with some residual fluctuations that are very tiny. And so the question is, how do you test this in detail? So far, we've seen only the largest indication of patches on the sky, nothing to do with galaxies. So where do we go next? Well, so this is where we go next. Now, in this picture, this was the prediction, basically, in the underlying line here, okay, of what we should get in terms of all different length scales. This is one particular scale, and now we're adding up different scales. And so for the smallest scales, these are the smallest scales on this side, the radiation smooths out the matter fluctuations, and then there's a range where and what you can see is the prediction that's in the form essentially of sound waves early on, imprinted as the universe suddenly cools down at last scattering on these fluctuations in the radiation. And so this was a prediction made some in the 1960s by independent groups of cosmologists, this solid line. And the early experiments were shown here. These were done in balloons or on the ground with enormous error bars. So you can see they gave a general indication of a peak, okay? And one experiment flown in a balloon was the one that basically made the major discovery of this peak around 1992 2002 or thereabouts, just after this epoch, where the error bars suddenly got rather smaller for one experiment. But it was to take another decade before things really improved. And so this shows you how the sequence of satellites and you had to do
He
this.
just wants to fix some.
Okay.
Do you have a phone in your pocket?
No. Is that? Should I talk?
Okay.
Okay, is that okay? Is that better?
Yeah.
Okay, good. Sorry. Okay, so here's the sequence of improving satellites. So 1990 was the launch of the COBE satellite, which is later, 2 years later, with these indications of the first fluctuations, a small telescope, low resolution. Then in 2001, the second satellite came along called the Wilkinson probe of the cosmology background. The data analyzed from the next satellite, and so you can see this is the Planck satellite. This was a European-led project. This was a US-led project, but with Europe playing a role in both, of course. And in this Europe-led project, the Planck satellite, you could see precisions of fractions of a degree, and the fluctuations, you see cold, regions slightly colder than the average, regions slightly warmer than the average in these different colors, and we're looking at fluctuations of millikelvin. And I should say the overall radiation that was discovered by Penzias and Wilson was 3 Kelvin, okay? So by going to sensitivities of the millikelvin, we could finally begin to pick things up at much more accuracy and begin to see these fluctuations. And so here we have this same prediction of the fluctuations, now with the error bars over plotted, and you can see, one can see the effects of the radiation smoothing out different mass scales, and these are sound waves in the early universe frozen out when the universe suddenly gets cold after the electrons and protons recombine, redshift 1000 or thereabouts with the residuals here. So the theory really looks remarkable, and it doesn't take, it turns out that this model is a really simple fit to the data. And let me just update you now. First, I'll show you the 2 satellites. So this was the WMAP satellite, which took data in this period, and the Planck satellite, which took data over this period with somewhat higher resolution and a wider frequency range. And from the Planck satellite, here is the map of the tiny fluctuations in the sky. Now, what they also did was they looked at the polarization of these fluctuations, and that was remarkable too, because the polarization is ultimately going to be the key to cosmology. In this particular map, you're seeing the effects of dust mostly in the sky, which polarize the radiation. These are polarization vectors, and they have really important information because it's, in a way, an independent map of the sky when you're looking polarized light. And so it basically confirms the overall picture and has more information about the foregrounds, which you have to eliminate. It's like, wiping a car window screen free from all the dust you accumulate when driving in India or anywhere else for that matter, and have a clear view. And the polarization is the way you do this. And then finally, the gravity in the universe lenses actually the fluctuations, distorts them slightly, and this is a map of, and that gives you a map of the dark matter. So this is just the mask from the Milky Way, you just ignore that, and so here is the dark matter distribution inferred with its structure in it that represents large structures. So that's the interesting part of the story, and what is maybe the most remarkable thing of all is that the fit of that line I showed to the data is described just by 6 numbers. So 6 numbers describe the universe, and that is remarkable because you have many thousands of pixels, millions actually of points on those on the sky, and many thousands of points on your data curve, and you can fit all of that with 6 numbers. So that's remarkable. What are the numbers? Well, there's a number that describes the density of dark matter in the universe. That drives the gravity that controls the fluctuations. There's a number that describes the amount of baryons in the universe. They control us, the stars, the mass that we see, the luminous mass. There are the sound waves, those wiggles that you saw. And so there is the scale, the wavelength, if you like, of those sound waves, and their amplitude. Those are 2 important numbers. And then finally, the shape, the overall shape of the spectrum, it has some slight tilt to it in power. And then finally, when the universe reached roughly a redshift of 10 or so compared to the 1000 that you see in these maps, up till then it was a plasma. The radiation didn't scatter, passed freely through it. Then at some point it recombined, became ordinary hydrogen, made the galaxies, and that really is an important factor, because at that point you can you have to control how much ionizing matter there is between you and the source of this radiation, and that gives you a blurring effect. We call that the effects of the reionization of the universe. So that's another parameter. Also controls the fluctuations. So with these 6 numbers, we now have 1%, better than 1% accuracy. The one thing that's still slightly uncertain is the effects of the recent epoch smoothing from reionization. That's not quite as accurate, but that will change in the next years as we do better experiments. And so you can describe all this data with 6 numbers, which gives us a lot of confidence that what we call the standard model, which is the solid line in when I showed you the spectrum, the power in the data, that fits. You just adjust 6 numbers and you get a beautiful fit to the observations. And so that suggests that we're on the right track, that what we call our standard model is working pretty well. It's rare in physics that you get this much success to fit these complex maps of the sky, but this is where we are at the moment, doing percent precision cosmology, that is measuring the parameters of the universe that describe its expansion rate, its density, all the components in it, to levels of a percent. I mean, parenthetically, when I began in cosmology, and long after actually, and throughout the 1990s, we were talking about 50% uncertainties. I remember having a debate with my colleagues at Berkeley at the end of the 1990s actually, and we were debating whether the universe had a factor of 10 uncertainty in its density, and that meant the universe could, if it was denser, eventually reach a maximum size and recollapse, and if it was less dense, keep on expanding forever. Incredibly important thing to know, but we couldn't tell the difference in the predictions of those models. Now we've done a bit better. We're still not completely sure of the answer, but we have measured things with much more precision. Okay, and so the name of the game in what we do with the microwave background is the advanced precision cosmology. And so in the rest of the talk, I'm going to show you how we're going to do better in the future with the microwave background or whatever else. Okay, so I have to be a little frank here. I realize that not all of my colleagues are totally happy with the current status of the microwave background as fitting our standard model of cosmology. There was in fact a meeting at the Tata Institute in Mumbai just 2 months ago, completely on anomalies in cosmology. So I'm going to show you an example of anomalies that make you worry if we're on the right track. Does our fundamental model developed by Einstein, Lemaitre, basically, Friedman, does that model, which fits the data so well, are there flaws in this fit? Are there cracks in the edifice of cosmology? And so, we have our cosmologists sitting around the table discussing the Big Bang and the standard model, and we may have an elephant in the room. So, what do I mean by this? Well, first of all, let's just look at the data. So this is the reproduction of the data, looking now at the power spectrum, the power in the data of the fluctuations on the sky. And it does seem to give you a beautiful fit when you include all the recent data. The solid line is the prediction, and then on top you see the theory. The data's binned, you don't see all the data, you see bins of the data, but the point is it fits incredibly well. However, when you look in detail at the maps, Some of my colleagues get a little bit, I could use the word excited, maybe that's the right word, or desperate or intrigued, because they see certain regions which are slightly brighter, hotter or cold than the average. Now, blue means cold and yellowish means warmer, and we're talking about differences of a fraction of a thousandth of a degree Kelvin. And so if you look around the whole sky, you find that there's one notorious place, not number 5 on this figure, called the cold spot, and there are a couple of other cold spots, and there are a couple of hot spots. And these, it is argued, are unexpected if, with all this physics coming from the early universe, these are not predicted by the Standard Model. The Standard Model says everything should be highly Gaussian and randomized, you know, the fluctuations should be randomized, but this seems to show there are deviations. And so there are a number of these deviations. Here is, on the figure I just showed you, here is another one. I didn't comment before, but let me comment now. And that is, if you look at the very largest angular scales, and that's on this side, you see a very low point, but with a huge error bar, of course, because of various systematics. So this point does not fit on the curve. And then my colleagues look at other anomalies. I won't tell you about them in any detail. And in general, all of them typically, you know, you predict when they run, basically they take the data and they do the predictions of what the sky should be. And because there's intrinsic variance when you deal with finite numbers, they run thousands, hundreds of thousands of maps of the sky, okay? And they look to see how they might differ one from another with Gaussian statistics, okay? And so what they find, of course, is that some of the points that I'm talking about are actually on the edge of some distribution, right? Okay, so that's the worry that we're dealing with, but the trouble we have is this, that while, for example, here there are 5, and maybe there's at least one more, different so-called anomalies, and I should say that there was this conference at TIFR just 2 months ago, solely on anomalies like this. So some people take it very seriously, but then the question is, are they, you know, if you add them all up, fine, that suggests there might be a problem. But the fact is, all these anomalies are correlated with each other. You know, we just don't know how in any detail, but it simply isn't just that simple. You just can't add them together. And so the bottom line is that when we look at this and try to say what statistically is it, we say that all of these anomalies are at most 3 standard variations, some 2, some 3, and in physics, the cast iron rule is never believe anything unless it's a 5 sigma result. And so there's simply no reason to take these at the moment seriously. So my conclusion is, well, you know, we have anomalies in the microwave background. Should we be panicking at seeing cracks in our standard model? And I think the answer right now is no. Now this may change tomorrow, but right now I think that's the answer. Okay, now let me move on to what we're going to do next, okay? And so this is the sort of things that we have to do in the future, we will do in the future. So, but I should say that telescopes, satellites are fine, they're wonderful things. They cost lots of money. Typically the ones I showed you in the range of hundreds of millions of dollars, that sort of cost. But the next step is going to be bigger and better satellites or experiments on the ground, which is going to cost far more. So what you have to do is argue that you need some, because you're competing with other scientific projects. In astronomy alone, we have a very compelling lobby for discovering if we are alone in the universe, right? Looking at exoplanets. We have to have an experiment that is just as compelling as that. And that means, and equally in other fields of physics, compelling reasons for doing launching expensive experiments, such as the next particle collider, which will be, many billions of dollars, which is roughly going to be the cost of, of order the cost of some of these major space projects that I would like to see. So what sort of guaranteed and above all compelling science do you need? Well, let me give you one example. I talked a bit about anomalies, but this is something much more fundamental, and that is, the question is, the microwave background has a spectrum, and it's the most amazing spectrum that we've seen in physics. It's a perfect black body spectrum. However, everything we know about the universe tells us it cannot be a perfect black body. Our fundamental theory predicts that there were things going on early in the universe that should leave traces, deviations from the spectrum, and that's guaranteed, okay, from the physics as we understand it. So that's an example of a compelling science return for a fundamental experiment. Unfortunately, it's, again, incredibly expensive and incredibly long term, as I'll argue, and it's going to take a long time. We'll get there eventually. And then finally, there's another issue, which I'll come to at the end, which is we're probably running out of what we can ever do with a microwave background, which is the title of my talk. The reason for that simply is that if you look at the sky as seen by the Planck satellite, for example, there are of order 1 million pixels that make those maps, something like that. And that means that when you extract data from 1 million pixels on the sky, there's a limit to the precision you can get, roughly 1/√n or something. So the only way to do much, much better is to use other data channels. So one data channel I'll mention briefly now is galaxy surveys. So we're entering an epoch now where up till now we've had typical surveys of galaxies with distances from their redshifts, which have millions of galaxies, okay? And so this current generation of surveys means that you're roughly as powerful as the microwave background in terms of looking for deviations from the standard model, or tests even of inflation, which is really one of the main goals, which I'll come to in a moment. The future, we'll talk about surveys, I'll explain this to you in a moment, which involve, well, first of all, the next generation will be hundreds of millions of surveys, and that's going to do better, but there may even be something beyond galaxies. So that's what I want to try to explain next. So the next generation of galaxy surveys, starting now already, will do far better than the microwave background. It may be we go to what I call 21 centimeter modes. I'll explain that that's the dark ages, really, and that will take us much, much further. So we'll see how that goes in a second. Okay, so the microwave background, where are we, what are we doing? So the big news last year was that we had 2 major ground-based observatories working under design to actually do much better than the Planck satellite towards testing our theories of inflation, which that did not, as I'll show you in a second, not really manage to do. Unfortunately, one of those surveys got cancelled. That was the one at the South Pole, for reasons beyond the control of any scientists. But the other one is ongoing. It's called the Simons Observatory. It's in Chile, on the Atacama Plateau, at a height of some 15,000 feet or so. And it involves, you can see the telescopes so far constructed beginning to take data over here. There's one large telescope, 6-meter diameter, and a number of smaller half-meter telescopes. The small telescopes have a wide angle, they map the sky, the bigger ones go deep, and so they complement each other, and they're going to, with hundreds of thousands of detectors in their focal planes, be able to get high precision maps of the microwave sky that go to angular scales that complement, take us beyond what was done so far with Planck satellites. And I'll show you the cosmology that we hope to get from that in a second. So that's the Simons Observatory, funded partly privately by the Simons Foundation and partly by the American National Science Foundation and NASA. So half and half funding, basically. And so they're planning to finish their data by 2035. This parameter, which I call TRS, I'll explain that in a second, it's a measure of the polarization. It will be roughly something between at least 10 times better, maybe 30 times better, anything we can do now. And it's the essential parameter for testing the inflation theory, which we'll come to in a second. Okay, so that's one new direction. The other one is in space. Why do you need to go to space? Well, on the Earth, even at Chile, the high Atacama plain, where there's little water vapor in the air to basically, scatter, absorb some of the microwaves, you have a much clearer view. And also you can study the whole sky with your telescope pointed anywhere. Whereas if you're on a terrestrial site, you're limited in where you can look at the mountains, whatever, are around you. So the LightBird telescope, which is basically a JAXA, Japanese mission, is planned for launch by 2035. It will achieve roughly the same sensitivity as the Simons Observatory mission, but its advantage will be that it will go to the largest angular scales. Remember, one of the anomalies I showed you was that quadrupole and those large spots, anomalies on the sky. All of those it will do much better because it is an unimpeded view of the sky, and it will complement what we can do with high accuracy from the ground on smaller angular scales. So we need the two together, that's for sure, space and ground. And so the LightBird will have many frequency bands. It's cryogenic, it's cooled in space, which is a real complication, but that I think we know how to do now. It'll have 4,000 detectors. You notice that this has 4,000. The Simons Observatory had 120,000. The reason is that a detector in space is worth, maybe 100 times more than one on the ground, or something, some factor like that, because you have all this atmospheric stuff on the ground to work your way through. So you just, you can get by with similar detectors, but much more sensitive in space. So that seems to be that's what will be happening if we're lucky, because we still have to build the detectors for this telescope, and that's a matter of intense controversy at the moment. Japan does not have all the technology that is needed, and they're busy planning on how to go forward with that now. But for the moment, it's going ahead for launch by 2035. Okay. Okay. So, what's the future then? That's the future for the CMB. And what do we want to do in the future? Well, we want to have much more precision on our parameters. So I said that we have these numbers in cosmology, the key numbers that define the universe, to 1% accuracy roughly. Well, as in all of physics really, you build a better experiment to get more accuracy, right? So the next generation has to improve that by at least a factor of 10. You want ultra precision accuracy, okay? So otherwise, no one's going to, approve all the funding you need to build this experiment. And then ultimately, you want to do something more than just precision. Okay, it's all very well, and we do a lot of this in physics, measuring things more precisely. But I think many of the physicists in the audience know that if you want to build a future circular collider, there are many people that argue, well, there's no guaranteed new discovery coming from it. Why should we bother? And so that's an argument you have to counter. And it's even more important in cosmology, which has a smaller community basically, and has to just incredible expenses. And so what the ultimate thing that you need in cosmology is a test of the inflation theory of the beginning of the universe. And I'll show you how we hope to do that. Okay, so this is the current status of the fluctuations in the microwave background. And what I've done here is I've included all the polarization measurements. So the temperature fluctuations that you saw on those beautiful maps are basically here. You can see the oscillations, the damping of the oscillations that I showed you about, temperature maps. And on large scales, you notice there's enormous uncertainty, and that's simply because you have a limited number of independent scales in the sky. If you want to look at, a fraction of a degree, you have many patches on the sky. If we want to look at 10 degrees, which is roughly where those large purple lines begin, you have far fewer. If we want to look at 90 degrees, where there's that anomalous point with huge error bars, but below the standard line, then you just have to think of some clever way of doing better than that, okay, with better data. And so what you also see on this graph is the polarization maps. Well, the thing called EE is one type of polarization that basically is produced by fluctuations, essentially by dust intervening. You have to clean the sky of dust from the Milky Way into stellar medium, and dust is elongated particles. They scatter the light, as we all know when we use polarized sunglasses. So you have to clean the system of all the foreground dust, and it's essential to do this via polarization. Polarization is the only way to do this. And so that has been measured. You can see even when you can look through the dust at the fluctuations, you can measure the intrinsic polarization of the fluctuations. Now, the fluctuations produce polarization because the electrons that are scattering the light from the beginning and giving you these fluctuations, they're moving. There are these sound waves going on this last scattering surface. And so that means the electrons go from being at rest, they go faster as the sound wave reaches its maximum, and then it slows down. A wave oscillates like this. And that effect of the oscillation gives you a polarization, and that's what you can measure. And though that's a wonderful test too, if you can look at the intrinsic fluctuations. Okay, so that's the idea which may be left over, which come from the early universe after you get rid of the dust. So that will help you understand better if you can measure the motion of these oscillations that we see in this curve over here. If you can measure not just the actual hotspots on the sky, but the polarization, which reflects their motion, then you get a better grip on the accuracy. So it gives you more data and then ultimately what you want to do is you have to work your way down to the signal from inflation, the primordial fluctuations that you might hope to see, which are intrinsically polarized, and they're the ultimate test of inflation. Why are they polarized? Because the inflation of the universe, which involved this dramatic expansion, basically shook the universe up while it was expanding and induced an intrinsic polarization. And that polarization is different actually from that produced mostly by dust, because it's due to gravity waves, and gravity waves don't compress, they shear, okay? And this is the principle of gravity wave detectors. And because they're shearing modes, they're distinct, much harder to detect, and that's why we separate these into EE modes, the compressional modes, and the shearing modes. And you also use these modes. Shearing is what gravitational lensing does for you when you amplify images. We use that also to sort out the effects of lensing, which again are a problem. All the dark matter masks or distorts our view of the fluctuations. The dark matter between us and the last scattering surface. So we have to get rid of that too. So all of this you can do by looking at these, what I call here the BB modes. And then peeking through, I should say, at the very end of this is the primordial signal. That's these heavy dashed lines. And this is the intrinsic one over here that you're looking for, incredibly weak. You have to clean all this up. This is our best current experiment called CLASS, operating in the Atacama Desert, which is designed to look really at the larger scale fluctuations. These are larger and larger fluctuations on scales, and it's clearly orders of magnitude away from measuring this. So that's the problem right now. We're a long way. We can get down to a few percent maybe of what you need, but we have to, it's a huge improvement. We need to get to a few percent of that to do better. Okay, and so that's the story there. And so just to highlight, that's the region of this, what we have to tackle, and you can see that involves doing so much better than we're doing now. These error bars have to be reduced to be able to reach this over here. And so this is the future, if we can do that somehow. Okay, and so the question is, can we do this actually? Okay, so notice that this curve over here, this prediction, is defined by r equals 0.1. So that's the ratio of the strength of the inflation modes to those called by the standard modes that make the galaxies, which compress. So the inflation modes stretch things out, gravity waves. That's the signal of the end of inflation, a definite guaranteed signal in many models of inflation, but not all, unfortunately. However, then that is something that you want to aim for, and we're sort of still a long way from that. And this is sort of the latest data that we have at the moment. Okay, so why am I so pessimistic about the microwave background actually measuring anything to do with inflation? So this is our state-of-the-art predictions. All of these colored lines denote predictions from the shaded areas are different combinations of theories. And these lines are predictions, okay, of certain models of inflation. Now, what I want you to realize is that we're looking for this number R, which is the ratio of the compression, of the shearing modes, the inflation mode, ultimately, on the very largest angular scales, to the compression mode. And I showed you that with 10%, 3% is something where we're at the moment. This is probably where we are now over here, okay, from these data sets, so maybe 4%. But to test inflation, you have to measure something. And what I think you can easily see from this figure is that all of these various curves and even the data, there's no lower limit, okay? So we don't have a minimum prediction of inflation. In fact, if you take a conservative, I would say, point of view, you would say that inflation generically is untestable, at least within the limits of what we can do with polarization, because there is no guaranteed prediction of it ever giving us a signal in, say, the few percent level, or 10% level, 1% level, even 10th of a percent level, which is all we can ever measure. Okay, and the majority of the models may take you much lower. So that's sort of the crisis we are in cosmology. There's no actual lower bound on the signal from inflation, which is what I call the tensor mode here. Okay, so now let me take you on a quick trip through the future of cosmology. And this is sort of to show you that we're doing amazing things in cosmology. So I'm just going to flash through these. So these are galaxy surveys. This is the microwave background I just showed you. So these are measuring, on the left we're measuring the density parameter of the universe, and the way we can fit the model of Lemaitre, Friedman, etc. That's this parameter, microwave background. But again, we can get more precision with the future. This is where we are at the moment. Microwave background, no lower limit, all these experiments on the way, maybe. And as far as the dark matter goes, well, we have experiments that have found nothing so far. So it's a major part of the universe, but it's so weakly interacting that even going to looking at the gamma rays, that's this particular, or going deep underground to find evidence, or even colliding particles together, enormous energies, no evidence so far whatsoever that any of these will lead to any success. Nothing guaranteed. And even if you change gravity, which some of my colleagues will want to do because of that, they believe that there are issues to do with not finding dark matter, for example, that doesn't help either. There's just so much, no guaranteed return. And that's the problem indeed, that there is no guaranteed breakthrough from any of these experiments. So again, I've showed you experiments from the new generation, current and new generations of galaxy surveys, microwave background, dark matter searches, direct searches, indirect searches, future colliders, giant colliders, and changing gravity. Nothing is guaranteed. So the question is, how on earth do you persuade the funding agencies to support you? Okay, it's a great thing to do to get more precision, but if you don't have a guaranteed return, you're not going to compete with the groups wanting to discover life in the universe or whatever, okay? And so we need a compelling return for very expensive science projects. So that's my philosophy here. So history is interesting. In half a century, 50 years, we went from 50% uncertainty to 1% precision. The next generation ongoing now will take us to 0.1% precision. Okay, so that's happening, but that doesn't guarantee science returns. The question is, I think we want to do better. We want to increase that precision to have some hope of getting to testing inflation. And I'm going to give you two examples in cosmology of where we know there's a guaranteed return. So the first one is this amazing result from the Planck satellite, the COBE satellite. This is the best black body spectrum ever measured, okay? These are 400 sigma error bars, okay? And so it's a perfect black body. It shouldn't be a perfect black body because the universe is full of things like galaxies and stars and whatever formed them, okay, by gravitational processes. So there've got to be deviations. We haven't seen them yet. There are predictions of these deviations, that this is the black body curve. There should be some deviation, okay, but we're a long way from finding that. And so here is the reason for looking for that deviation. So we call this deviation, which is predicted in the standard model of cosmology, it's the same effect that gives us the sound waves, the damping of the sound waves in the microwave background. This will affect to the smallest structures earlier in the universe that basically are fuzzed out by the radiation, but that leaves energy behind. There's friction from the small, and the small structures are a fundamental prediction of the Big Bang theory, of what we call the bottom-up theory of structural formation. Cold dark matter has to be there if we take our model at face value, a simple prediction. And so right now, what we have are only measurements in the yellow here on microwave background and large-scale structure. In the future, what we want to do is two things. One of them is looking at this distortion, which will explore this part of the spectrum. And the second I'll come to in a moment is looking at the 21 centimeter seeds, the gas seeds of the structure in the dark ages. So those are the next things to do, and they'll be much more powerful, and that will test fundamental predictions of modern cosmology. And again, just as the radiation gives you powerful things to look for, so you can get many trillions of modes from looking in the dark ages. I'll expand on that in a second. So the problem with the microwave background is that we had an experiment proposed twice. It's a Fourier transform spectrometry in space designed to look for spectral deviations from the microwave background. It was rejected twice. There is a current project proposed to do this, wait for this, in 2065, okay? It'll be the next opening for a large mission by the European Space Agency. And so that will be a similar experiment, and it's designed to do the things that this experiment couldn't do, maybe go down from being just 100 times better than COBE to 1,000 or 10,000 times better. And so that will get us to measuring. So this is the microwave background. These are various predictions. This is the limit from the COBE experiment. And so this is sensitivity curves of what you will be able to do in the future. And to me, so what we're doing is predicting this effect to measure this major building block of the standard model to predict there are many small things. It's a bottom-up model. So that's, generally speaking, roughly where this line is, somewhere in the middle here, between this and the yellow region. But the ultimate goal, which I think is incredibly exciting, will be to measure the physics of the hydrogen way back in the first 100,000 years of the universe. And that is recombination of the hot plasma to a cold plasma. That gives you lines. It's the bread and butter of current astronomy. We measure recombination lines. Everywhere we do anything, that's what we measure when we study galaxies or whatever. And to measure that from the universe itself, I mean, it's, first 100,000 years will be amazing. And so that would be the ultimate future of this mission, which unfortunately will not have an opening to 2065 because of competition from basically the exoplanet communities and other communities for very good science projects, but they've already been given priorities. Okay, right, so the microwave background is another remarkable thing, is that this was an early experiment, a balloon experiment, that measured that the microwave background fluctuations were incredibly Gaussian, right?
And so that's remarkable. This is data with high signal to noise. This is all the data. And so of course, the noise, all the systematics give you non-Gaussianity, non-random type things. But ideally, if you have a signal from the early universe, you probably want to be looking at deviations, but not due to the intervening, messy physics, but from the beginning. So first, now we've not seen this so far, but it's a prediction of the models basically. And what we see is a highly Gaussian field. There's no trace of any, weird things happening. And when we measure maps like this, we measure Gaussianity in the initial fluctuations to an extreme degree. So what I'm going to argue next is that the inflation theory, there's one robust prediction, more robust than gravity waves, in the sense that we can experimentally get there, as a guaranteed return, that is non-Gaussianity from the beginning. So that's the final part of the story. It's a robust prediction, but it's a very, very small effect. So what are the chances ever of getting that? Okay. It's back to the moon. The only way to do that is by putting telescopes on the far side of the moon. And so this is an ongoing project. Why do we want to go to the moon? Well, basically, you want to look when the universe is 1/50th of its present size, between then and a 100th, which means you have to go from 21 centimeters, how we study hydrogen by the spin-flip transition all around us, to wavelengths of 10 meters or thereabouts, 30 megahertz. Unfortunately, this involves basically the same frequencies that we use, in radars and television, FM radio, whatever on the Earth. So terrestrial interference is a disaster, and so is the Earth's ionosphere, which these low frequencies can't penetrate. So the only place you can go to do this is to go to the far side of the moon, and there, if you have a huge array, just of dipoles actually, each dipole must be roughly 10 meters long to be sensitive at these low frequencies. You just put lots of them down and make an interferometer, and in principle, if you have hundreds of thousands or millions of these, you can basically map the whole sky at exquisite resolution. And so that's easy to estimate how to do that. The far side of the moon, where there's no ionosphere to block your light, on the near side, there's no interference from Earth, radio interference. You have to go well within the far side to avoid spillover from the Earth, this radiation. And when you do that, you've got the most radio quiet environment in the entire inner solar system. So it's the place to do radio astronomy, to look at the beginning of the universe. And are we going to do that? Principle, if all goes well. So that will happen. We don't know what the timescale is, but it's being seriously considered by the Indian Space Agency. So why are we doing all of this? Why am I so excited by testing the beginning of the universe? Well, it's very simple. What we've measured so far are fluctuations in the temperature. That's what I mean by this symbol delta T over T, okay, over here. Okay, so what is exciting is the non-Gaussianity, the differences. That's actually a unique prediction of the inflation theory from the very beginning. And you can see that if I look for a term which essentially is quadratic in delta T, this is just a constant that tells you we don't know what that is, we're trying to find it, then it will be a non-Gaussian signal. The square of a Gaussian is non-Gaussian, right? And so there's a prediction from my colleagues that work on inflation theory, and it is that fairly generic inflation models should give you FNL values that are basically 1% corrections to the delta T we've measured with a Planck satellite. So that's interesting. You've got to do much, much better than Planck. And you can't do it with a CMB because that is very near the limit of what we can ever do with a CMB. So that's why we're excited now by the Dark Ages experiments. So to summarize, currently from the microwave background, we get numbers of order 10 for this FNL. That's the upper limit. We have 1 million modes on the sky. The future, the next 5 years, is the new generation of galaxy surveys. So they will get numbers, they'll measure billions of galaxies and 100 million redshifts. That's what you need, 100 million redshifts. So with 100 million modes, if you like, you can do 10 times better in noise than the CMB, and we predict they should be able to get to FNL values of unity. Now maybe some inflation models will take us there, some will not, but the generic case, we have to do much better. Only trillions of modes will do the job, and that means getting to FNL of 0.01, and those are because there are so many, in principle, hydrogen clouds, they're precursors, they're fluctuations, at redshift 50 in the dark ages. So that is sort of the story there. To me, this is the ultimate proof of inflation. And so, let me summarize. Perspectives for the future. I think multi-messenger cosmology is the name of the game. It's microwave background plus the dark ages, which involves low frequency radio astronomy from the far side of the moon, plus the stochastic gravity wave background. I haven't talked about that, but in principle is another way of probing the inflation theory directly with gravity wave experiments. Now we're very far from that right now, but again that's a future thing. And then finally, one thing I haven't talked about is that there are, I mentioned briefly, anomalies. Well, there is a big debate that goes on about the expansion rate of the universe. There are communities that disagree on that for different techniques. And so this may be another crack in the facade of cosmology, the standard cosmology, or maybe systematics of the data. We simply don't know. So this is all for the future, and this is where we're going. And above all, I want to emphasize, it's for the young generation, because we're talking about experiments of timescales of, many, many years. I mean, if we do a spectral distortion experiment, the slot available for that is 2065, the next call for an ESA large class mission. And if you want to do something on the moon, then maybe 20, 30-year horizon is what you should be looking at for these experiments. So I think this is a strong message. The young people have to get involved in this now, and they'll be leaders in the future. Most of us making this pitch won't be around to see the results. Okay. So large arrays, incidentally, we have these future arrays proposed both by NASA, certainly in design form, also by China for 2040 in that time scale. So again, the future really is beckoning, and that seems to be where we're going. So thank you.
Joe, for a wonderful lecture. We have time for some questions.
Of course.
Yeah.
Thanks for the nice talk, Joe. I have one question. You mentioned that there is no guaranteed returns for inflation using CMB and large-scale structures.
Yes.
Initially. And finally, when you showed the slide from the FNL, delta F
Yes.
10 power minus 2,
Yes,
0.01.
yes, yes.
But can you say that it is a guaranteed return? Because if it is completely slow roll, 16 epsilon h is R. And that means that if we are not able to see R with light bar or anything, we will not be able to see FNL as well, because FNL is proportional to epsilon as well.
Well, sure. So the question is, I'm sure you can design models which will give you nothing. But the question is, we want to look at the generic inflation space. And my impression is that the Mulder-Steiner type argument is more than just, single mode inflation, multi-mode inflation, etc. So,
yeah. Okay. You are saying it can distinguish between single field and multi-field, etc.
For example, yes.
Yeah. Okay. My question was basically, let's say it is a very simple model, single field
Yes.
inflation, and we are not able to see it at 10 power minus 3, R equal to 10 power minus 3, then that means that epsilon h is less than 10 power minus 3 divided by 16, means 10 power minus
Yes.
4. And then FNL will be similar. So
Right.
from there also we do not have...
Well, again, you want to get down to 0.01, which is not so far away, right?
Yeah,
That's the ultimate goal. So I think you can get there. I mean, if you could give me models with 0 or 10 minus 3, I would say forget it. But I've not seen that in the literature. So I think we're okay for the CMB. And I think the argument you gave for a particular case is, you have to ask what generically does inflation predict? And you can go back to polarization. What is that prediction? I don't think it's within, R ratio is within the observable range of 10 to the scalar, generically, yeah.
Yeah, so you were saying about the 6-parameter model that
Yes.
is an excellent fit to the
Yes.
CMB, right? And the 6-parameter model is practically fixed at the physics at the last scattering, at
Yes.
recombination. So the universe at recombination fix everything, right?
Yes.
And this universe now predicts that later on at each redshift, different observable. And amazingly, when you do experiment, we exactly match with this observable, right? So there is nothing then, I mean, after decoupling, there is nothing free, except some anomalies that we are talking about. But if you forgot, I mean, aside.
Yes.
So anything, the universe which is at 380,000 years old,
Yes.
whatever the universe is, this is more or less fixed, right? After that, there is nothing in the universe that, because whatever that is predicting, we are actually, all the other later observations are kind of fantastic matching.
Yeah.
So this is a sort of very strange, because there is nothing, I mean, it is unlike to other things. Here, very old universe, everything is fixed, all the late time physics, everything is, we know already at
Yes, yes.
what will happen. So what is your comment?
So I disagree. There is not nothing. I mean, the region below redshift 100 is full of gas that has started cooling more than the radiation. So initially, redshift 1000, the gas and the radiation are coupled together. Then the baryons cool more effectively, so you have a temperature difference. So suddenly, you can see the baryons in a shadow against the microwave background, absorption. And the first thing we have to detect, we haven't done it yet, is the global signal, because it happens everywhere you look. So the monopole is going to be the first test. And then, moving forward 10 years, 20 years, we'll do arrays with high angular resolution and look for the fluctuations. So that's the second step, really. Getting the monopole is critical, but it's predicted to be there. I think there's no way around that.
No, I'm saying that it's predicted to observe, right?
It's predicted, not observed, absolutely.
Yeah.
But we're putting the experiments together now.
But the prediction is mostly by this redshift around 1000, right? The lambda CDR model, whatever.
Yes.
So unless we get something observed, which is very much beyond prediction.
Yeah. Well, we've got to look. Experiments are the goal, right? So, yeah. Yes.
So it was a great talk. So I have one question. So when you are describing about the CMB spectral distortions, like in the early 2000s, the TRIS experiment was conducted at 610, 820 and 2.5 gigahertz in the low frequency range, below what is expected by big C.
Yes.
So like when you mentioned when we probe the dark ages in sub gigahertz regime, we are sensitive to more to the 21 centimeter fluctuations. But could the same experimental data be repurposed for using to probe the low frequency regime, the rallying state of the CMB spectrum to check for the new type of distortion?
I think the problem with going to the low frequency part of the CMB is just the enormous foreground from the galaxy. So it's very, very difficult. We have data points, but getting the spectrum in detail the precision is just not adequate. The error bars are large.
So when you try to argue that in some distortion physics, then you just kind of say that there might be many things happen, and can you just be slightly more specific what exactly you mean by that? Because you see, I mean, when you say many things happen without a very specific science goal, then it would be also very difficult to convince someone.
Yes, that's right. So the problem is that as you leave the dark ages, you leave them because the first stars are forming. And so, and the first black holes are forming. And so these emit lots of radiation, and they affect the temperature of the hydrogen, and there is no longer any clean prediction. So by going to higher redshift, it just means lower radio frequency, you can avoid all of that completely. So there's a window of radio frequency between probably 10 megahertz and 30 megahertz that fits the range between 30 and a redshift 30 and 100. That's what you have to go for. There's a clean signal. Unless there's some totally bizarre theory like weird dark matter particles that mess this up, but then you'll learn something new too. But
Hi, Joe.
Yes, sorry.
Thank you for the very nice talk. So you mentioned CMB anomalies, and taken individually, most of them don't reach some 5 sigma threshold for significance. But if you think about the fact that all of them, occur, that we see all of them together, not just one, does that add to the statistical significance? And secondly, if it turns out later that these anomalies are really there, not just systematics, what fundamental assumption that goes into our standard model might be
Yeah. Yeah.
driven.
So I think that's exactly the problem. You can't add them up because all of these anomalies must be correlated in unknown ways. They're not independent measurements, okay, completely independent measurements. So, and we don't know how to assess the degree of correlation between them so far. The only thing you can do is run, and the people have done this, is run many, many Monte Carlo simulations of the sky and look to see how, whether even now and then you can obtain one of these weird features. And the answer is yes, a few % of the time you obtain them. And that's after running 100,000 simulations. What I think is missing is that no one so far has been able to run a slightly non-standard maps of the sky, such as maps of non-Gaussianity and primordial non-Gaussianity. Those might give you more chance for getting the fluctuations, or even if you want to get to be slightly more exotic, you know, models that are slightly anisotropic, Bianchi models in their expansion rate, weakly Bianchi. Models like that might do a better job for you. We don't know because no one has tried this yet, but that to me is an interesting direction to go in next.
So this is just a follow-up of the first question regarding the last part of your talk about measuring non-Gaussianity as a signature of inflation. If this goes ahead and one tries to measure it and we don't see anything, will you kill inflation?
I think that if they can get the sensitivity limits down to 0.01 for FNL, which is not going to be easy, it's going to take many years because of the foregrounds, I would be very worried about inflation. But I'm sure theorists in this room will be ingenious enough to come up with models.
This is
Yeah, that's right, that's right.
At which point we should start discarding inflation as a mechanism for...
Yeah, what I think we're missing now are inflation models that predict in FNL values between 0.01 and 1. There's a whole range there that we could be studying, and we really need a whole suite of models to decide, what limits can we set in the future. At the moment, we don't know. So.
Thank you very much for the great talk. Coming back to Gaussianities, I do think that there is the unique prediction for FNL, right? Because it is linked to NS, to the
Yes.
spectral index. So we have measured NS, so we have actually a precise prediction for FNL single field models. So it would be great if we really can reach the threshold that you were mentioning through 21 centimeter. So this was just a comment also related to the questions.
Yeah.
And then I have one for CMB anomalies. So what do you think could be, from also an observational point of view, the best way to eventually increase, if they are real, the statistical significance?
Well,
Can, for example, 21 centimeter be another way to eventually test them and to make their, let's say, to make more robust their statistical significance?
Well, there I would say galaxy surveys, the new generation, which can go much deeper than previous one, could look at things like the cold spot and these other, few anomalies I showed, and see if there is any interesting excess in the galaxies on these scales. That would be very interesting. Right now with the cold spot, the problem is that attempts to do this in the literature have not gone deep enough to the other side, as it were, of the cold spot, or if there is another side, right? So we don't know. But I imagine much better galaxy surveys that would be one interesting step in the right direction. And the other thing I think should be done to explore more general sequences of sky maps that have some deviations from our standard model, and see if they can more easily produce these, these weird effects. My favorite would be someone to simulate an FNL of one model, for example. Make sky maps. No one has done that, to my knowledge.
The last question.
Thanks for the talk. This is regarding the dark ages signal here.
Sorry.
This is when the dark ages signal from prognosticated signal. So we know that the foregrounds will be a problem. So my question is, can the ground-based radio interferometers operating at those frequencies, for example, LEDA or Nenufar, can the foreground models from them can be used for the measuring the dark ages signal from the moon?
Yeah, I think ultimately you'll be cross-correlating everything we get our hands on, including the CMB, with the new 21 centimeter skyfires, whenever they come in. So cross-correlations will be the way to go. You obviously, ultimately, you want to track, the Planck spots, fluctuations in the 21 centimeter too. There should be some correlation. That would be very hard to do because the noise levels are complicated. Ultimately, that will be a test.
If there are no questions, let's thank Mr. Joseph again.
Thank you.
Joe?
Thank you.
Thank you very much, sir.
Thank you.
Thank you.
Thank you so much.